Okay, so in this section, we're going to relate everything we have learned so far, and more precisely, or more specifically, we're going to learn how to characterize the invertible matrices. So let's look at the first theorem. So suppose that A is a square matrix, so this is the important part. Then we have all the statements from A to L are equivalent. And this means all the statements below are all true or all false simultaneously. So suppose that the given matrix A is an invertible matrix, then it is equivalent to tell that the given matrix A is row equivalent to the n by n identity matrix. And for part C, well, let's look at this example. So suppose that A is 3 by 3 matrix. Then if you REF the given matrix, then we know that it's row equivalent to the identity matrix 0, 0, 1. And now we can tell that we have pivot positions for each rows, or equivalently, the number of pivot positions matches with the number of rows or columns. So A has n number of pivot positions. And if you analyze this reduced matrix, then you can tell that, well, there is no free variables. That is equivalent to have the homogeneous matrix equation has only the trivial solution. Then if you split this matrix equation into the vector equation, then it is equivalent to have the vector equation given by a1 x1 plus a2 x2 and so on plus an xn equals to 0. So here a sub i's are the column vectors of A and x sub i's are entries of the given vector x. Then this equation has only the trivial solution, which is equivalent to have the column vectors of A are linearly independent. And furthermore, if the columns of A's are linearly independent, then we know that the linear transformation associated to the given matrix should be 1 to 1. Okay, for part G, we know that we have pivot positions for each rows, which means the non-homogeneous equation ax equals to b has at least one solution for every b in Rn, or in fact, we know that the solution is unique because you can simply multiply by the inverse matrix of A for the both sides. So x is given by A inverse times b. And if the given matrix equation, the non-homogeneous equation, is consistent, then we know that the columns of A span Rn, and if so, the linear transformation defined by the multiplication by A maps Rn onto Rn. Okay, and if the matrix A is invertible, then there exists an inverse matrix C such that, well, if you multiply the inverse matrix on the left, we get the identity matrix. And also if you multiply the inverse matrix on the right, we get the identity matrix as well. And lastly, the transpose matrix of A should be invertible as well. And this is because, well, if A has an inverse, say B, then A times B equals to the identity matrix. Or if you take the transpose operator for the both sides, then we get AB transpose equals to I transpose. But we know that the identity matrix is a diagonal matrix, which gives you I itself. But AB transpose equals to B transpose A transpose. So A transpose has an inverse as B transpose. So one thing that you want to note is that all these things are equivalent only if when A is square matrix or n by n matrix. So if you use the theorem above, we can easily determine whether the given matrix is invertible or not. So suppose that A is given in this way, then we can tell that we have pivot positions for each rows, or there are 4 pivot positions matches with the number of columns and the number of rows. So by the theorem number 1, part C, we can tell that the given matrix A is invertible. So here, you want to note that we don't need to find the inverse matrix of A to verify whether the given matrix A is invertible or not. Suppose that T is a counterclockwise rotation about the origin by the angle theta, and A be the standard matrix of T, so T of X is defined as A times X. So let's pause the video and determine whether the given matrix is invertible or not by using the theorem above. Okay, so let's solve this problem together. So we know that T, the rotating process, is reversible. Or in other words, for given B in R2, we can find X such that B sits inside the image of the vector X. Or in other words, we can tell that this matrix equation has at least one solution. So by the invertible matrix theorem, IMT, part G, we can tell that A is invertible. A linear transformation T is said to be invertible if there exists a function S such that it satisfies S of T of X equals to X and T of S of X equals to X for all X in Rn. So recall that this is really similar to what you had in the inverse function, like f of f inverse of x equals to x, and f inverse of f of x equals to x. So we call this S as the inverse of the given linear transformation T. So here, the theorem states that the linear transformation T is invertible if and only if the standard matrix for T is an invertible matrix, or in other words, if you define S to be A inverse times X, then that function satisfies these two conditions. So let's prove this theorem. So in this direction, we have to assume T is invertible. Then we know that for any B in Rn, we have T of T inverse of B. Well, this should equals to B itself. Then this implies that T of X equals to B has a solution. Because we can say, well, T inverse of B solves the equation, right? Then this tells you, given transformation T is onto, but note that this was one of the conditions on the inverse matrix theorem. So by the inverse matrix theorem, part I, we know that the inverse matrix A inverse exists. On the other hand, suppose that the inverse matrix of the given matrix exists, and then we're going to prove whether the given associated linear transformation is invertible. So we need to define the inverse transformation. So let's say S of X to be A inverse times X. Then we can tell that S of T of X is the same as S of A times X. That equals to A inverse times A times X, which gives you just X. And T of S of X is the same as T of A inverse of X. That equals to A times A inverse times X. That gives you X. So because T and S satisfies these two conditions, so we can tell that so T inverse exists, and more precisely, we have T inverse equals to S.